Good morning, dear students. Today we will discuss about corrosion on metal surfaces as part of my MSc Third Sem Industrial Chemistry coursework. As you all know that corrosion is a natural phenomena that convert a refined metal or a pure metal to a more chemically stable form, as refined metals or pure metals are highly reactive. Due to this corrosion, the metal surface got converted into either its oxide, hydroxide or sulfide form. The process of corrosion results into gradual destruction or loss of material, and it occurs either by a chemical or an electrochemical reaction of the metals with the environment. The isolated pure metals are highly reactive, or we can say that they are in highly excited state, and it is because of this reason, because of the high reactivity of metals, that metals are always found in nature in combined state, except very few metals like noble metals. All the metals are obtained in combined state, either in the form of carbonate or oxides or sulfides. And during the process of extraction and refining of metal, extraction from the ore, we have to invest money, energy, and after that process, we convert that metal into a pure metal. And when the metal gets converted into pure metal, it again becomes reactive because it again goes to the highly excited state. And when this metal is being used in some structure, it again start reacting with the environment because of its high reactivity. When it reacts, it changes into a high stable or low energy form, which is known as the combined state. So we can say that isolated pure metal are highly reactive and highly excited state, while combined state of metal is a low energy state or more stable state. Now we can define the process of corrosion as any process of destruction or deterioration of metal and consequent loss of metal through an unwanted chemical or an electrochemical reaction of the environment. Or in simple words, we can say that corrosion is basically loss of metal from the surface because of reaction with the surrounding. And especially oxygen, moisture and other gases react with metal to cause corrosion. It is basically a reverse of extraction of metal that I just mentioned. The most common example of corrosion is the corrosion of iron, in which the corrosion product iron oxide is also known as rust, which is reddish in color. In case of copper, the corrosion product is green in color and it is known as basic copper carbonate, CuCO3 plus CuOH twice. Now we'll discuss about the gravity of corrosion. Although the process of corrosion is very slow, but the losses associated with it are very massive. First of all, you can see that because of corrosion, there is a destruction or deterioration of machine because of loss of metal from the surface, loss of destruction of machines, equipments, pipelines, and other metallic structures or products. Now, when these destructed machines or machines that are not working properly has to be repaired or we need to refabricate them, it involves monetary issues. We have to invest money again. Therefore, the worldwide estimated estimated loss due to corrosion is around $2 to $2.5 billion annually. But beyond this loss, monetary loss, there are certain other losses that cannot be converted into monetary values. For example, if a metal structure is being used in making bridges, buildings, apartments, factories, schools, and due to corrosion and loss of metal, some of the structure may undergo failure, or it may result into the loss of life as well, which can never be converted into monetary basis. And therefore, the losses are massive and very, very, very serious. Corrosion is basically divided, or you can say broadly divided into two categories: the dry corrosion or chemical corrosion. On the other hand, we have wet corrosion or electrochemical corrosion. Dry corrosion occurs by direct chemical attack of gases like oxygen, halogen, sulfur dioxide, hydrogen sulfide, etc. It may occur either at low temperature or at high temperature in absence of moisture. And since no moisture is there, therefore it is known as dry corrosion. Metals like alkali metals and alkaline earth metals corrode at low temperature, while rest of the metals corrode at high temperature. The basic reaction of corrosion is an electrochemical reaction. The same kind of reaction takes place in electrochemical cell. In case of corrosion, the metal loses electron to acquire a positive charge. The electrons thus released by the metal is being accepted by oxygen to form an oxide layer. The overall reaction is given in the slide, where the metals on the surface react with oxygen to form a metal oxide. Depending upon the type of metal, it acquires +2, +3, +4 charges. So this is it. Some basic information about corrosion. As you have already studied in the previous lecture, that corrosion is broadly classified into two categories: the dry corrosion or chemical corrosion, and wet corrosion or electrochemical corrosion. The dry corrosion is mainly the type of oxidation corrosion. In this type of corrosion, there is a direct attack of oxygen on the metal at low as well as high temperature. At low temperature, certain metals like lithium, potassium, sodium, beryllium, calcium and strontium undergo corrosion, while other metals do not. But at elevated temperature, almost all metal undergo corrosion, because temperature enhances, or you can say supported the rate of attack of oxygen on the metal surface, which ultimately increases the rate of corrosion. Now we'll discuss about the mechanism of corrosion, how corrosion, especially the oxidation corrosion, takes place. It always starts from the surface of the metal. Oxygen present in the surrounding environment react on the very first layer present at the top, at the surface of the metal structure, and convert it into metal oxide. Now the layer of metal oxide, or you can say the layer of oxidation product, is formed on the surface, which act as a barrier for further corrosion, and therefore this layer restrict corrosion under certain condition, which means that further corrosion of the metals which is present below this layer depends upon the type of layer. Clear? So if the layer is smooth, non-porous, then it will completely restrict corrosion. But if the layer either evaporates, or if the layer has some pores in it, so because of those pores, the metal comes outside and undergo corrosion, or the oxygen can move inside and corrosion can be continued. So depending upon this oxidation product, depending upon this corrosion product, or you can say depending upon this oxide layer, the further corrosion can be decided whether it will occur or not, and what will be the rate of that corrosion. Clear? When the metal is attacked by oxygen, the metal that is present on the surface is attacked by the oxygen, metal immediately start, because of its reactivity and its electropositive nature, it start eliminating or releasing electron, converting into positive charge, and then those electrons released by metal are accepted by oxygen to form the oxide layer. One thing to be noted down here is that a layer is called a film when its thickness is less than 300 angstrom, while if its thickness is greater than 300 angstrom, it is known as a scale. Now we'll discuss about the type of oxide layer or type of corrosion product. If the oxide layer is stable, which means that it is fine grained in structure and adhere tightly to the metal surface. Further, this layer is impervious, or you can say non-porous, and because of its non-porous structure, it prevents further corrosion of the metal. This type of stable layer or stable oxidation product is formed in case of aluminium, lead and copper. Then the other type of layer is known as unstable layer. In case of unstable layer, the layer decomposes immediately to convert back into methane and oxygen. and thus corrosion is not possible, because once metal react with oxygen to form oxide layer, the oxide layer decomposes back to form metal and oxygen. So only the top layer will be in a reaction with oxygen, while the layers which are below under that layer remains protected. This type of corrosion occurs in case of gold, silver and platinum, and therefore since they are not corroded, they are known as noble metal. The third type of oxide layer which is formed is known as volatile layer, and this volatile layer means that the layer, as soon as it is formed, it is immediately evaporates, exposing the metal present below it, and therefore the corrosion rate in such in such volatile layer below case is very high. The example is molybdenum oxide. And the fourth type of layer is known as porous layer. Porous layer means these layer, although they have good thickness, but they have pores, or you can say it is a porous layer. And because of that, there are two possibilities. Through these pores, either the metal atom comes outside or the oxygen can diffuse inside. Oxygen molecule can diffuse inside. But since the size of oxygen molecule is high, there is more possibility that the metal atom generally diffuses outward and they react with oxygen to form the corrosion product. And therefore, in case of porous layer, the corrosion of the layers that are present at the bottom continues to take place. Now I would like to discuss about a very important rule which is known as piling Bedworth rule. In case of piling Bedworth rule, it states that if the volume of oxide layer is as large as the volume of metal from which it is formed, then the layer is protective or non-porous. If the volume of oxide layer is as large as the volume of metal that has been used to form that oxide layer, then the layer is protective or non-porous. Example, lithium, potassium, sodium and magnesium. However, on the other hand, if the volume is less than the metal volume, if the volume of layer, oxide layer, is lesser than the metal volume that has been used in this oxide layer, then the layer formed is known as porous or non-protective layer, and such type of layer is formed in case of aluminium metal. So this is all about the type of layers that are being formed and piling Bedworth rule. In the next class we will start electrochemical or wet corrosion. Thank you very much.